the course. So I will say some words, yes, and some short summary of what we saw yesterday. So basically, we saw how to use R Studio, and also we have started with the concepts for parallelization, right? And something that maybe was not clear enough, right, was that why do we need the batch scripts, right? Or why do we need R script if we can use R Studio? So if you remember, we start R Studio after loading the modules. And we mentioned that we should use R Studio just for lightweight tasks. And what does it mean? It means that we can use it for editing our scripts and for computing some lightweight tasks like doing some visualization, data visualization after we get the data, right? So, but it's not recommended to run the scripts. For instance, yesterday we saw this write a serial script. And if this is lightweight, then we can run it as usual, right? But otherwise, you prepare your script. It's called serial.r. And then you will need a batch script, which is the one provided here. Right? And here you specify your project. We saw that yesterday. And this is one way to run the script, right? And this is a second way. So some people say this is more flexible. And yes, I think this is a kind of recommended way to run our scripts. And this is for data production, right? So use R Studio for lightweight tasks, and this is type of scripts for data production. So once you have this script, then just submit it with SBatch. Yeah, and yes, today we will see more concepts about the parallelization. And at the end, we will take a look at the best practices for R in an HPC cluster, such as doParallel at PDC or Kepner-Kaise at HPC2N. So I think that's it. Henric, you can start.
Thank you, Pedro. I start by sharing my screen. And then I'll just do the presentation here. I guess you all can see it.
Yes, that's correct.
Good. Yesterday, we went through a little bit on how to use optimized function in R to increase the throughput of serial computation in R. And today, instead, we will go through what this course is all about, meaning parallelization in R. And some of the concepts I showed you yesterday will be useful here as well. So today, this lecture will be about different executor types in R and how about using optimized libraries. And I also will talk about the parallel package, which enables you to do shared memory computing, and as well as for each package, which will enable you to do shared and distributed memory computing. So let's first talk a little bit about execution types. As you all know, and you're all acquainted with, default R, if you start R by default, it only uses serial computing. There are some functions that are using parallel computing as well, but we'll go through them a little bit later. Instead, when you want to do, the easiest way to do parallel computing is to use shared memory parallel computing. And that type of computation uses either threads or POSIX threads. You can use something called sockets, and very rarely something called OpenMP, which is a multiprocessing and multi-threading. Why I mention this is also that even if usually you run on your laptop, and that today most processors on different laptops and on stationary computers are also parallel. So they have a number of cores. For example, on this laptop I'm running now, I have 8 cores. So you could use these techniques on your laptop as well and get an increase in speed by just making your functions parallel. Then is something called distributed memory computing, which Pedro went through yesterday as well. And that is more for the clusters, where you kind of use different nodes to move your data to different nodes and compute it in parallel there. I would say, in general, distributed memory computing in R is not used that much because it shows a really poor scaling. But let's go through using optimized libraries. And why I want to mention this is that this is a very easy way to, instead of parallelizing all your function, you can use optimized libraries, and you don't have to do anything in your code, but you can get a lot of faster computation. Or, for example, linear algebra functions in R will be a lot faster by using the basic linear algebra subroutine, BLAS. And these subroutines provide a standard building block for performing basic vector and matrix operation. So you do a lot of matrix computation, then you will benefit by installing these BLAS and LAPACK libraries in your version of R. So BLAS is usually installed by default. It's not always the case. But default BLAS is not optimized. And to optimize it, you have to install OpenBLAS. And installation of OpenBLAS can be performed in different ways. If you have Ubuntu or some Ubuntu analog, I, for example, run Linux Mint on my computer here, which is an Ubuntu analog. You do just sudo apt-get install libopenblas base. In OS X, you can use brew to install OpenBLAS, and you install it. In Windows, it's a bit more complicated, and you have to use something called Microsoft R. And here's a link to it in this presentation, which you can read through and install it if you would like. But what is the difference then? If you go into your RStudio or R and look at it, before you installation OpenBLAS, if you print something like LA library, you will see where the library for this is installed. In this case, you see that this is the installation path of it here. If you install OpenBLAS, you see that this kind of entry here, like OpenBLAS pthreads. That means that OpenBLAS has been installed and has enabled something called POSIX threads. And that will show you that that now BLAS will be run using shared memory computing. And I can show you a little example of this, which I made on my computer a year ago. And for example, this is a function here which simulates a matrix of 1 million observation by M prediction, generate an outcome Y. And I compute the least square estimate on linear regression coefficient when regression response Y on the predictor matrix X. So this is just an example function to do a lot of heavy matrix operations. And if I use this function and run it on like start time, sys time. I do it 100 times and print the difference. When I did it before installing OpenBLAS, the execution time was 16 seconds. But when I did it with optimized BLAS, OpenBLAS, the execution time was 7 seconds. So just this simple thing made the calculation time reduced by roughly 50%. So that's an easy way to parallelize the code without parallelizing it if you do a lot of linear algebra expressions. So that was that. Now we start talking about the parallel, how to do parallel computations. In R, there is something called a parallel package. Parallel package has to be installed, but it's in a crime repository. It's really, really easy to install it if you don't have it. But sometimes it can be installed by default, and on each PC2N cluster it is installed. And the parallel package contains many functions. And it also has a function in it that detects the number of cores you have. And if you set logical to false, then it just goes to the physical cores. But instead set logical to true, then it detects the hyperthreaded cores. And if you don't know what hyperthreaded is, that's a process when a core is split in each physical core is split into two virtual core, which are known as threads. And so meaning that you will have hyperthreading, you get double the amount of cores. So you get, for example, you have 4 hardware cores, then we'll get 8 hyper-threaded cores, which you can use. So when you do detect cores without anything, then it just detects the logical ones, which instead you do logical, the hardware ones. But instead you do logical true, then you get the one the hyper-threaded as well. So I mentioned it in the second slide, what types of calculations there are. And now I want to go a little bit in detail regarding this. And there are 2 types of parallel calculation that I want to talk about in this lecture. One is forking, like what we're calling threading as well, or POSIX threading. And that is actually that it kind of forks, what it does, it forks the process. It's faster than sockets because it copies the existing version of your entire works that exist in each process. And it's very, very easy to implement. But the negative thing is it only works on POSIX systems, meaning Mac, Linux, Unix, and BSD, does not work on Windows. So if you're working on Windows, you have to use sockets. And because the processes are duplicate, it can cause issues specifically with random number generation. But it can also cause problems like for example, race condition that Pedro mentioned yesterday. The other way for shared parallel computation is using sockets. Sockets has the advantage of work on any system, including Windows. So, and each process on each node is so unique, so it will not cross-contaminate. So it kind of duplicates the data and the process at the same time. And that way it avoids the race conditions that we talked about earlier. But as each process is unique, it will be slower because you have to move the data back and forth as well. And things as package loading or moving data has to be done in each process separately. And various variables are defined in your main version or does not exist in each core unless you explicitly place them there. And I'll show you some example of it later on in the presentation. And it's more complicated to implement. What I can say also is that socket, now this is for shared memory computer, but socket is very close when it comes to distributed computing because it uses kind of the same technique in socket programming when you do, for example, using distributed memory computing. So now some examples, because I know when I will teaching myself different kind of codes, the easiest way is to learn by example. And now here's an example of forking. The functions that you can have for forking, for example, is maclapply, mclapply, and mcmapply. And as you can see, these are the function or the parallel function we used yesterday. And here's an example on how to run it. You use a library parallel, you do detect the number of cores. In this case, I use detect cores without setting logical, which will detect the hardware cores. And then I decrease it by 1. And why I decrease it by 1? Because I don't want to use all cores. I want just all cores minus 1. So 1 can be used to still doing other stuff, like, for example, looking at your mail or running our studio and so on. And then you can use all the other cores to run your computation. And then you run maclapply. For example, in this case, maclapply, I add 1 to 100, which creates a list in here, function fun, MC cores equals number of cores. So this will kind of run lapply on a list of 100 with the function fun and with the total amount of cores in this on this computer or laptop minus 1. But remember that is not always faster, like we talked a little bit about yesterday. Small task, if you're using it for small tasks, the overhead of scheduling a task and returning the result can be greater than the time to execute the task itself. So sometimes the actual initiation of starting parallelization can make the process in general take longer time than the actual process itself, and then it's really not worth it. Instead, here also I will, as I talked about, I show you a socket parallel example. In this case, you also can see that we're using lapply, but the functions are called a little bit different. They're called par-lapply and par-supply, and you have to add something called cluster as well. And here as well, I can decrease the number of cores by 1 for not interfering with the master core, master thread, I mean. In this example, it's a little bit more complicated, but not by much. Example, library, parallel, number of cores, do exactly the same as they do when forking, but here I have to create a cluster. So I make a cluster with the number of cores that are available, and then I use par-lapply cluster variable list of 100 function fun, and then when I have finished this, I have to stop the cluster, in which I do the stop cluster and then the cluster variable. But what also makes this even more difficult is that, as I mentioned before, these are separate processes, and therefore you have to move your data to the separate process if you want to run it. So if there's a specific library you need to load the package within the process, then you have to run a command called cluster eval q. So after you set your make cluster with and you have returned the variable, you do cluster eval qc, and then you add library name, meaning this will add that specific library to the process and that you're running at the moment. Also, variables are not present within the parallelization and must be passed. So if there are specific variables you want to run in this parallelization needs to be used, then you have to do something called cluster expert first. So this cluster X will see an X that moves the variable X to the cluster. And then you register the variable X on the cluster by using cluster eval q CLX. So this will register it. So this is a way to pass your variable into that specific process that you're running. So it's a little bit more complicated than running on forking stuff. So that is all I wanted to talk about regarding PAR-LAPLI and about the uplift function and how they are parallelized. We will go through them a little bit more later on because we will have the labs in this aspect. Another way is to parallelize your code is using the for each package. The for each package, it's a very flexible package. It works for serial, it works for shared, and it was also distributed memory computing. And in many ways, it's a very easy step to start with, as you can just implement it in a for loop. So how does it work? Here is an example which I showed you yesterday, and it's the default data set of CO2 concentration in parts per million from 59 to 97. And I create a list of values for each year, like I did before with X, and then I run for each. I equals X, which is my list, and then I write % to % mean Y, I. And this for each command here will go through the whole list and print the mean. But it, as I said before, only works in serial. How do you then parallelize it? To parallelize it, it's really, really easy. First, you have to use these libraries. Library parallel, library for each, library doParallel. I forgot one thing here, is that library for each, which I mentioned in the middle, has to be added here as well. I will correct that later in this presentation. But just to be aware of it, you have to use a library for each here in this example as well. But you need the library parallel and library doParallel. And it's very similar to OpenMP. It works in that kind of manner. And if you want more information about for each, there is a link here which you can read up on. But on towards the examples. As I said, you need the library parallel, library for each, and library doParallel. And then you need to know how many parallel processes are available. And then you use a command called get doParWorkers, which will return how many parallel processes are available. And then you have to register doParallel to register the number of processes. And then the only thing you have to do is substitute your %do% with %doPar%, and that will switch them to serial computing to parallel computing. An example of this looks like this. In this case, the libraries, parallel, for each parallel, I then split my data sets into the years for the list. I register doParallel like this, and for each equals X doPar mean. So that is the only thing you have to do. Add the extra libraries, register the number of processes, and switch do with doPar. So as shown here, it's a very easy step to test out your code in serial using for each for all your lists, and then see that it works in the serial, and then just add a couple of libraries, then use the doPar instruction here instead, and then everything will be parallel instead. But there are some, in this case, the register doParallel here that uses all the processes that are available. So, but there are ways to defining the number of processes. And one of these is instead of using the same kind of way that the socket approach did when using LAPLI. So first thing you do is make cluster and the number of processes. And here you can decide the number of processes you want. For example, if you laptops run 8 cores, you can say, oh, well, let's run on 4. So make cluster 4, and then you have the number of processes we need. And then instead of just saying nothing is the register doParallel, we set register doParallel with end processes, which is the one that our cluster. And the same as we did before when parallelly, when we have finished everything, we have to stop the cluster. And then we do that, stop the cluster and end processes, the number of processes that we'll be using. So this is a way to define how many processes you want to run. And this is something will be used later on as well. So for each has, I will not go through them all, but there are one parameter which I think in for each is very useful, and that is the combined parameter. So if you, for example, want to use the combined parameter, you do for each, this is I equals 1 to 100, comma, and then point combine and type C. For example, do, this is a serial example, function E, and what that actually does is it returns an array if I use the C1. But I can also use other kind of combined elements like cbind returns a column matrix, rbind is that returns a row matrix, and plus or star sign can summarize the result or multiply the result. So, for example, this one combined plus is very useful. For example, if you do a lot of computation, then I want to calculate the average of it all, and then you can use this combined plus and summarize all your results, and then afterwards you can, oh, I know 100, and divide what I got with 100, and then you get your average of it. So that's a very easy way to kind of computate, to use average of it all. So a couple of working examples. Equivalent to Lapply, x mean. Instead of using Lapply x mean, I can do x split like this for each one to equal z and %do, and then just calculate the mean of it. And if I want, for example, return an error mean, as I showed before, I can do comma, point combine C, and it's exactly the same, but we set that one here. And then what it does, it will return an array instead of a list of means. And I showed you before also, well, if, for example, you want to calculate the mean of them all, you can do combine plus there, and then just you get the sum of it all here. These are serial examples, and if you replace do with doPar, then you will kind of parallelize them all. I will not go through in this presentation distributed memory computing. You can use distributed memory computing using the doMPI library instead. That will not be installed on your laptop, but I think it is installed on the Henric. And why I will not go through that is because, first of all, R seldomly scales above one node on a supercomputer. Second of all, when I had this course last year, there were lots of questions and people really didn't understand the value of distributed memory computing. But that said, I show here an example, an easy example on how to use for each and using doMPI. As you can see, there is not much that differs from the doParallel. You use the library doMPI instead, and you register doMPI instead, and then you close the cluster. But then you have to use MPI quit as well. There is also something called RMPI in distributed memory computer, which is a little more difficult than this. But this should be, if you're interested, you can try it out and run it. So this is what I wanted to say about distributed memory computing. And now it's the time my lecture's ended, and I want you all to kind of do some labs and try this method out. The first lab is as you calculate pi using MC-Lapply. If you did your lab yesterday, we used the calculate pi algorithm, which I show here. And we used Lapply to calculate the pi. In this case, I want you to calculate pi using MC-Lapply instead. And I also want to try it with different number on cores. You can run your code on your compute laptop and on your cluster, or both if you want. And then I would like you to calculate the speed up with increases number of cores. So you'll be using what we talked about yesterday about timing how fast your code is, and then start with one core and then increase the number of cores and see how much speed up you get for each increase of number of cores. I would like you to, in this lab, also do the same, exactly the same, and calculate the speed up by using PRACE and compare MC-Lapply and PRACE. Do you think it will be faster? Do you think it will be slower? Oh, it will be more or less the same kind of ballpark when it comes to how fast it is. And as a stretch, if you have time, also use for each that I just show you. And then here you can also use calculate pi by using parallel for each instead. And so I'll just leave that slide on. If there aren't any questions, you are free to start. And please try it out on your laptop first as well, before trying out on your cluster.
I will just say that I just checked, and doMPI is not installed on Kebnekaise, but it should be easy to install yourself.